So just briefly remind you what we did. So we considered the formulation with generalized coordinates. And generalized coordinates is some vector, some dimension. So it's a vector of coordinates which describe uniquely. So they have to describe uniquely the system, the position of the system. So they describe position of all material points in our case, no? In some way. So then what we know is that if you want to write equation of motion, you just write usual Euler-Lagrange equation. Euler-Lagrange equations, which is that formula that you already can start to remember. So the n coordinates and equations, and what is L here? L here is a Lagrangian function, which is always difference between kinetic energy and potential energy. So the T is a kinetic energy. Kinetic energy, it's a function of, in general, it can be function of time coordinates e velocities. But what is important is that whenever you give these values, its value should be exactly sum of all material points that we have by the mass multiplied by squared velocity divided by 2. So sum of these forms, which is each of them is a kinetic energy of the point of the particle. So summing them should give the value, which is exactly the value for the system with these coordinates and speeds. So this is not L, no? This is T. And then potential energy well, in general, it can depend on, usually it doesn't depend on velocities, right? So this is a usual restriction that we have. So that's it. And it's quite a convenient formulation because in principle, by material points, you can approximate whatever physical system with bodies, even with liquids and so on. So essentially, all what you need in this formulation is to find these two functions. Whenever you have these two functions, where first you always compute through the velocities, and second is given by modeling, so some model of interaction. So when they put them together, you don't care about details. You just write equations, and that's ready. So let's just do it a couple of times so you see how it works. So first, examples. The first example is the most classical, so it's pendulum. So what is pendulum? Pendulum is some point of support to which you suspend a mass, m. You say it's on a rigid rod, but rod has no mass. So it has such small mass that it doesn't matter. And then you say that there is a gravitational field. And that's a system, it moves. So how you write equation of motion? So first you should find generalized coordinates, a coordinate which defines uniquely the position of the system. So the usual way you compute the angle phi from vertical position, and of course it defines uniquely the position of the pendulum. Then you need to find potential, first kinetic energy. Kinetic energy should be sum of masses by velocity squared by 2. And we are looking for equation of, with respect to psi, So we only need to put contribution to this term, the contribution which depend on psi, right? All what depend on psi is the velocity of this mass, right? The other masses do not make a contribution. So for the pendulum, kinetic energy is energy of that mass by 2. And now you can find velocity. So if the pendulum has length L, then the velocity is L derivative of angle. So that's an expression. An expression for the, so this is, so you see it depends on psi dot only. No? And expression for the potential energy, this energy of interaction with what? Interaction with the Earth. Earth does not move in this formulation, so we didn't put it in kinetic energy. It will not give any contribution to the equation of motion, but interaction gives you contribution to the gravity gives you contribution to potential energy, and we wrote last time that it's mgh, right? Mgh. H is a vertical coordinate. So we can compute h, and we can compute it from starting from any point, right? So let's compute h from this point on, from the lowest position, and we know what it is. So the length, you can compute it for the length of pendulum and angle. So it's mj, and height would be 1 minus cosine L cosine, no, L 1 minus cosine psi. So 1 minus cosine psi is exactly this piece, right? How much what is the height of this pendulum over the lowest position? So we put them together. Put them together, so you get L t minus u, and it's L square over 2 minus mgl 1 minus cosine. So we have equation for the Lagrangian, and so the last step is Euler-Lagrange equation. Euler-Lagrange equation. So it's d dt, dl. So our generalized coordinates is psi. So d psi dot minus dl d psi equals 0. So this is an equation, and now you just put inside the Lagrangian function. So the derivative with respect to psi dot will be m to d dt m L square psi dot minus, and then there will be, so this is plus minus minus minus, so minus, and then derivative from cosine will be 1 more minus, so it's plus mgl sine psi equals 0. Then divide by the ml squared. So what will be left is psi double dot plus j over L sine psi equals 0. So that's equation of motion for the pendulum. So that's kind of course, you can write it in many different ways, but that's algorithmic way how you go directly through the variation principles. So the next example is already harder. So it will be not so simple to do it in a different way. Namely, we will consider the pendulum with a vibrating support. So what it is, with vibrating support, so let's consider the pendulum, which is now suspended. So it's say mass, length, gravity. But now the the place where it's suspended moves up and down. And let's put it in a way. So let's write the position is capital H of t. So this is a position, vertical position of the base. So we know how it moves. It does, and its motion is prescribed. No? So it's maybe very, very heavy. So it doesn't depend on motion of the pendulum. So it moves in exactly the right way, which we know for some reason, which doesn't matter. And now we want to know how the mass will move. So the generalized coordinate is the same. So whenever you know the angle, you know the full position. So now we need to do exactly the same procedure, but taking account that there is difference. So how you do, we put coordinate system. So let's put this lowest position of the pendulum to be origin. So we put horizontal coordinate x, vertical coordinate y. And then first we write what will be the position of the, by the way, not exactly this. So we put the horizontal origin at a place which corresponds to h equals 0. Okay, so whenever h capital equals 0, the lowest position will be here. But the support goes up and down. Right? So we cannot put, an origin should be fixed in space. So that's why we put a fixed origin in space. We know that it's exactly the position of the pendulum when it's in the vertical position and capital H is 0. And now let's compute. So first let's compute coordinates. Coordinates of the mass in terms of our generalized coordinates psi. So horizontal coordinates, it's sine of psi by L, right? So it's L sine psi. And vertical coordinate is, so first the same L1 minus cosine psi and plus h of t. Correct, no? So this vertical coordinate, so the same two coordinates that we had before, but we have to add capital H, which is position of the support. And now we need velocity, so let's compute derivatives. So here will be cos L psi dot cosine psi, right? And here y will be minus minus will be plus, so L psi dot sine psi plus h dot t. Okay. Good. And also, okay. So now we can find Lagrangian function. So Lagrangian is what? Lagrangian is first, we should compute kinetic energy. The only moving part is a mass. Right? The only moving part is a mass. So it's m over 2 by velocity squared. Velocity squared is x dot squared plus y dot squared. So this is a kinetic energy. And potential energy, we also know what it is mj by the height. Height in our case is y. So minus mjy. Okay. So this is, now we put everything inside. So this is m over 2. And I will be opening. So squared of the x dot square. So it will be L square psi dot square cosine squared psi plus this term squared. So let's open this square already. So L square psi dot square sine squared psi plus 2 dot and plus squared like this. Correct? I think yes. Minus mj. Mj and y is this, right? Mj L1 minus cosine psi plus h. Okay. So now you see this cosine squared plus sine squared give 1. And then keep only terms with psi and psi dot. You see, we only need to keep terms which depend on psi and psi dot, because after that we will write equation of motion. So everything which does not depend on psi and psi dot will just disappear. Right? So we can forget about many terms. So we can forget about this term, and about this term. You can keep them if you want, but they will not change equation of motion. But here they will give 0. Okay, so this is so these two together will give you m L squared psi dot squared over 2 point period. So these two terms. Then we have this term plus 2L psi dot psi h dot here minus with minus, no, give you plus. MGL. So that's it. So Lagrangian function at the end is, so let's put prefactor outside. So it will be psi dot squared plus over 2. Over 2 is here already. No. Just write it, putting this prefactor out. So phi psi dot squared over 2 plus 2 L squared 2 1 over L MH. I forgot m over 2 here, which cancels 2, so that's, sorry. See. So now ml, so it will be, there's no 2, it's h dot divided by L. Yeah, that's better. Psi dot psi plus GL. That's it. Yeah. Seems to be okay. And then we write equation of motion. So the Euler-Lagrange equation, which is just the same as for pendulum. But now it's a bit more tricky. Now you should be careful, because first you differentiate with respect to the derivative. Derivatives comes in 2 terms. So what you get is d dt. So we can forget about prefactor, right? Because it will multiply all the terms. So let's cancel it from the beginning. So from here it will be phi dot. And from this term it will be plus h dot over L sine phi. So this is the L the psi dot. And then psi comes also in two terms. So we have to differentiate them both. So it will be, division sign will give you cosine, so it's h dot over L, psi dot cosine psi. And this will give you minus j over L sine psi equals 0. And then we need to differentiate this expression with respect to time, which is a derivative along the trajectory. So you have to differentiate all the functions which depend on time. So this depend on time, h depend on time, and psi depend on time. So it will be three terms. So you get psi double dot. Then differentiate h twice, plus h double dot over L sine psi. And then psi, sine. So plus h dot over L cosine psi, psi dot. And then the next term, so it's minus h dot over L. Amount of zero. Then you see that these two terms cancel. And you get equation psi dot, double dot, plus j over L, 1 plus L. So that's your equation of motion. So see the difference between the usual pendulum and pendulum with moving, vertically moving support is you put this extra acceleration on the second term. And this is essentially what's known, I think it's called D'Alembert principle. So you essentially you substitute the this is not L, this is J. You substitute acceleration of gravity by true acceleration with respect to your full acceleration with respect to the moving frame. So there is another interpretation of this relation. Okay. So for example, if support moves periodically, harmonically, so let's put minus a cosine omega t. I put minus just to have plus at the end. So it's a is amplitude and omega frequency. So then you get the equation which is psi double dot plus j over L 1 plus, and here there will be second derivative, so it will be omega squared by a and change the sign. So it will be plus a omega squared over j cosine omega t. So that's a particular case of periodically moving support. So that's it. So this was the message, just to show how you write equation of motion in a way which is kind of more algorithmic. So you think less, and I prefer this method because it's kind of I'm more sure on the result than the others. So I will put the first collection of exercises. It will be exercises. So the idea that you do exercise, you solve them by, don't need to type, just by hand. The only important that it should be possible to read. So it's not always the case. No. So you write them, don't forget your name, and then either you bring me in paper or send by email. I will put there is my email, and then there is an email of the monitor. So please send to both. Actually, it's more important to send to him than to me. As I understand, most of the people see it online, so that's now the trend. So who is looking online can send also the exercises. It's all right. But now, if you want to be sure that it will be verified, then you have to be subscribed. Are you all subscribed? So it will depend on how many people are sending. So if it will be too many, then we will only look at the subscribed people. If not, anyway, I'm giving the time to send. But if you cannot send it on time, send it anyway later. So don't worry that much. So of course it's not so good, but so till Sunday. So the kind of standard term is please send it until Sunday. And there are 4 exercises. This is standard one that I always give. So first is so all of the exercises is to write all of the exercises is to write Lagrangian function and equations of motion, so all the Lagrange equations in given generalized coordinates. So just make this procedure. So the first is inverted pendulum. Inverted pendulum is just usual pendulum, but looking upwards. So this angle will be your generalized coordinates. So pendulum of length L with mass m, gravity, and that's it. So then the second example will be a bit harder. So it's a pendulum with a spring. So imagine a pendulum, normal pendulum, so that now it will look downwards. But now you don't put a mass just at the end of the rod. You put a elastic spring with mass at the end. So this spring is massless, so it's always straight. So it can move and also jump. So here we have mass m. We have 2 generalized coordinates. So in order to give a position, we can give you angle, and we can give length x. So the position of the relative to 0. So this is position at angle psi in position x. Also, we have a gravity here. And now the important part is what is the interaction. So interaction U will have 2 parts. So we will put gravity, mgh, so it's gravity. And also the other part of interaction is for the spring. So spring is will be k over 2 x minus x0 squared. So this is usual harmonic oscillator. So this is Hooke's law. So essentially, where this expression comes from is that x0 is a position where there is no force. Right? X0 is a position when there is no spring is relaxed. And this is the simplest expression that you can write, which will give zero force at position x0. Right? So remember, force is derivative with respect to x. That means that force with a minus. So force will be minus kx minus x0. So that's simplest expression you can do for which gives you zero force at position x0, and then it's the force is proportional to the deviation from equilibrium. So that's potential, and then that's a problem. Okay, and then C is a pendulum with horizontally moving support. So what it is, it's the same pendulum that we considered. Same angle as a generalized coordinate, gravity, length L. But now what we assume is that it moves horizontally with certain law. So you move the support, and then the question is, what is the motion of the mass? So what is the equation of motion for the mass? C, and then I can also give D. This is also a nice example. So consider the plane, and then you have a rigid floor. Which is given by some certain function depending on x. Right? So the smooth floor. And then you have again you have gravity. And then you have a very small ball of mass m, which is just rolling on top of it. We assume that no jumps. So assume that the rolling is such that it never needs to jump, just to make life simpler. So the question is, what is the equation of motion with respect to, so x is generalized coordinate, so find Lagrangian equation of motion. So one coordinate is enough, no? Since it's always rolling without jump. So having horizontal coordinates, you also have a vertical coordinate. So automatically, the question how to write equation of motion for the system. So that's it. So now we come to the next topic. It will be very important and interesting, I think. So the question about conservation laws. So that's another side of the symmetries. So we use symmetries in order to kind of shape the form of the Lagrangian. So to find to give some intuition of why the form of Lagrangian is like that. So these symmetries gave some restriction on Lagrangian, so we know the Lagrangian should be of this form, not of the other form. So now there is another role of symmetries, which is a relation between symmetries of specific type of symmetries and conservation laws. So the idea is that to special type of symmetries, having special type of symmetry, you are guaranteed that there is certain quantity was conserved, and that's a very universal rule, because essentially, probably we can say that all symmetries we know in nature, they're related to symmetry. All conservation laws we know in nature, they're related to symmetries. Or even if they're not, we don't know if they're related to symmetry, we expect that they are, so we look for the symmetries. So that's how some new conservation laws was discovered along the 20th century, and vice versa. So new symmetries was discovered, so first you find conservation law, and then you look for the symmetry, which is behind. So essentially the rule is conservation law and symmetry. Okay, so not any symmetry. So first we have to find what are the symmetries we're interested in, and before that, let's make a little bit more rigorous the formulation of what is a generalized coordinate. So generalized coordinates, generalized coordinates is a vector, is a point, but in fact it's not always point in Rn. And we will see it right away on example. So it's usually point on what's called n-dimensional manifold. So it's the same as a manifold. Think of it as a surface, smooth surface. So there is a, well, I recommend you to look at the mathematical definition, which is you can find easily in Wikipedia. But the simple view is that it's not n-dimensional space, but n-dimensional surface, like for example sphere n-dimensional. In fact, there is direct correspondence between the surfaces and manifolds. So manifold is essentially manifold is an n-dimensional object which is locally looking like Rn. So you can always look locally near each point. You can always write Q as coordinates, defined coordinates. So it's Rn locally, but globally it doesn't have to be. And then we can find very simple examples. So first example is the same, is a pendulum. So in a pendulum, our coordinate is not in R. It's an angle. So it's not any real number. It's a number on a circle, S1. So it's modulo. It's given modulo 2 pi. Right? So it's a circle. So locally, you can think of it as a number, but as soon as it changes by 2 pi, it's actually not a different point. It's the same point. The more sophisticated example is that example for the case, for this example B. So you see there were two coordinates. So exercise B. So here the generalized coordinates is angle and position. And position is positive. So it's manifold in this case is a product of the circle for the first coordinates and positive real line for the second coordinates. So that's second example. So you see they're locally near each point it looks like R2, but globally not. And then for example you can consider system of 2 points with fixed distance. So there is a rod which fixes 2 points. So they are given distance. They cannot come closer or at larger distance, and otherwise they move freely. So what would be what would be generalized coordinates? So you can put coordinates to the first mass. So the manifold will be coordinates to the first point, right? And then the second point depends on just on the direction of the vector. And direction of the vector is a point on the two-dimensional sphere orientation. So that I gave you several examples. So you see that it's you always can consider coordinates like in normal way, 1 to n locally, and this is how we always understand these coordinates. We always freely use coordinates, thinking that we just want to describe system nearby. So you always can give coordinates, but globally it's just a manifold. So just a slightly more complicated object than n-dimensional space. So now the next step would be to change coordinates. So we also discussed that different generalized coordinates has different advantages. So you may use, for example, coordinates which are coordinates of the material points, and they're useful. For example, they're convenient to find velocity. But maybe to describe the full system, it's not convenient to use coordinates, but more convenient to use angles. So there are different coordinates, and you can change. So, in one moment you use one coordinates, another use another type of coordinates. So what means change of coordinates? So change of coordinates, we will call it the function h. So change of coordinates mean that, for example, changing coordinates of the lower position to the upper position is to change, instead of psi, you'll consider now pi minus psi. So this is essential. And you see the coordinates, whatever coordinates you take, they always points on the same manifold, because this manifold defines the configuration of all configuration of the system. So change of coordinates, if you think it's always a function from a manifold to itself. So change of coordinates mathematically is just a change of, is a function which maps coordinates to its configuration space to itself, which means that with the same coordinates that we called one point, we now call another point. And there are extra conditions. So it's not just any function. So it should be what's called diffeomorphism. And this word means that h is invertible. So if you made this change, that you can make a backward change. So you have so it's 1-to-1. And then diffeomorphism means that its addition is so both e and inverse functions are smooth. Usually differentiable, but let's. By smooth, we understand the differentiable as many times as we like. So it's, in other words, diffeomorphism means that it's good function. So it's not some pathological change of coordinates. It's a function which connects one type of coordinates to another. So whenever you have these functions, it means that you can define new coordinates. So this was original coordinates, and then you define new coordinates. And then, as you defined, well, as an example, So for inverted pendulum, so this coordinate of the inverted pendulum, if you call it psi prime, it will be pi minus psi looking down. So you see, this is exactly h of psi. So this is 1-to-1. You can invert it. It's differentiable, so it's good function. Okay. So changing coordinates is good, but now we need to find change of Lagrangian function. In Lagrangian function, we have both coordinates and speeds. So we need to find new speeds. So the time derivative, and this is time derivative of this expression, and you can differentiate with respect to time. Well, it's a chain rule. So if Q is just a number, just a real number, then it will be, as you remember, it's dH dq q dot. But the same expression is correct in general if you think that this is a Jacobian matrix. So it's matrix of the derivatives dH1 dq1, dq1 dqn, dhn dq1, dhn. So derivative of all components with respect to all variables. And this is a vector. So the product of the matrix by the vector give you another vector. So this is a simple relation, and you see that this is a function of variables, of coordinates, and these are speeds. So we have a relation between the speeds as well, in a direct way, and then we can define new Lagrangian function. In new coordinates is by a single property that it has the same value for the corresponding point. So if you change coordinates, the Lagrangian function at the same configuration should not change. That's the only condition we had. So all what we need is that Lagrangian in original coordinates is the same as the Lagrangian in new coordinates for q prime equal hq, q dot prime equal h q. So that's a condition for how you find Lagrangian. So it just should be the same configuration should give you the same value, and then if you find from this relation the new Lagrangian, this is L prime. No? So if you find L prime, then you rewrite equation of motion, earlier Lagrangian equation in new coordinates. Okay. Okay. So now we can find. So this is kind of, I repeated all what we did before, but in terms of manifold and change of coordinates, like as a transformation on a manifold. So now we can define what is a symmetry. So how we define a symmetry? So we define a symmetry as a HS is a, so we will take a uniparametric continuous symmetry. If so, first is that we assume that H S1 so composed with HS2. So HS is HS, which was a map from M to M, right? So this diffeomorphism. So the family of maps with this index S, we will call it continuous symmetry if the first condition will be that HS1 composed with HS2 is HS1 plus S2. So this additive relation. What it means that if you first change, you take first change coordinates with HS2, and then change coordinates which is S1. Yeah? So the first coordinates, the second change of coordinates, it's the same as changing coordinates with a function with another index. So that's already okay. So the family of diffeomorphism with this property with this property, and the second property is that that Lagrangian is invariant with respect to any HS. So it means that Lagrangian function with the original coordinates is the same as same Lagrangian function written in new coordinates for So what it means is that, you see, when we change coordinates, we get new Lagrangian. And this means that, that after changing coordinates, you don't change function. It's just the same function. So this is this exactly condition that we used, remember, in deriving the Lagrangian equation for one particle from Galilean transformation. For the first and the second, for translations and rotations. So what we ask is that Lagrangian does not change, and then we have the group structure. So this second. So whenever we have this kind of uniperimetric family of diffeomorphisms with these two properties, we call it continuous symmetry. So the first observation that you have to say is that it does not apply to proper Galilean transformation. So why? Why Galilean transformations, which is changing to the moving reference frame, is not continuous symmetry? The second condition, because for Galilean transformation, it's not the same Lagrangian. It's plus this full derivative term. So that's exactly. So that's a stronger restriction. So we only here deal with the symmetries, which really do not change Lagrangian at all. So whatever you have these transformations, and this transformation depends on a parameter. So that's important. S is then it's all right. In principle, S can be real, or it's only important that it's real locally. So also can be angle. It's okay. So these two conditions. So what are the examples of this example? So first example also, which will be negative, is the example that we had in exercise C. So consider the periodic landscape. For example, cosine x. Cosine x, so here is 0, no, plus 1, plus 2. Then you have a mass moving on here with the gravity. So what you see is that h of x equal x plus 2 pi n for any integer n is a symmetry, right? So if you change coordinates by any period, you will not you will see that your Lagrangian will not change. But this is not a continuous symmetry, because parameter that we put here, n, is not continuous. It's just discrete. So this kind of symmetry, which is discrete, just changing by discrete numbers, will not work for this case. And what will work is, for example, when you have h is constant. If h is constant, then our transformation can be just adding any number, and it works. It's a symmetry. So this is okay. This is not okay. So that's the difference. So we need, so there are several ingredients. So it's important that it's continuous, so the parameter is continuous. It's important that it has group structure. It's important that it does not change Lagrangian. And whenever you have this collection of properties, let's formulate it. I put it there. Whenever you have this collection of properties, you have a very famous result. Which is called Noether's theorem. So Noether, Emmy Noether, she was a German mathematician, mainly working in the beginning of 20th century. And she did, essentially she was working essentially in the field of algebra. And this is probably the most known result because it's essential in the whole theoretical physics. So it's formulated and proves in a very simple way. So the formulation in words will be if a system has a continuous symmetry, HS, then there is a corresponding conservation law. So this is qualitative form how to say, and then just let's write a constructive form. So namely, the conserved quantity, the quantity defined as, so we have to define a quantity which is just functions, C, which will be function of time, coordinates, and velocity, so something, which we just directly derive through the Lagrangian function and symmetry. So it will be, so we have n coordinates. We always locally can write these coordinates. So then we differentiate Lagrangian with respect to velocity. And then what we do, we differentiate symmetry function with respect to parameter. And this is where we need that S is continuous. So we need to differentiate it. If it's discrete, like in periods, we cannot take derivative. So you see, this function will be function of S and Q. So in order to get rid of S, we put S to be 0. So we first take derivative and then put the S to be 0. And then it's now the function of time, the coordinates, and derivatives. So this quantity is conserved. Conserved means constant. Along any solution of the Euler-Lagrange equations. So you see, whenever you have symmetry, continuous symmetry, you automatically can just write equation. You know what will be conserved. And now we will see how this conserved quantity comes from Galilean group. So break deal. there was a question on the way about this derivative. So HSQ, you see, it's just notation for the function which depends on two variables, two arguments, S and Q, and we differentiate with respect to S. And certainly, I'm not giving very rigorous formulation, but certainly it implies that there is so continuous symmetry means that it's differentiable also with respect to S, and not only with respect to Q. Okay, so let's just first prove this theorem. So you'll see that the proof is actually rather simple. So all what we need is so what we will do. So we have a let's consider this HS as a change of coordinates. So let's consider coordinates Q prime. So fix S. So fix some S, and consider coordinates, new coordinates for some S, and then we also have new velocities. Right? So what we have is, so let's now take the expression so that, let's take this expression, but not for S equals 0, but for that S. For that S. So we take this expression, which is sum over n components dl dqi dot dhs ds. So let's take the expression, but not before putting S to be no. So let's do this and consider the corresponding Lagrangian with respect to primes. Okay. So let's write expression for that Lagrangian in primes, but remember, so L is the same. So this condition gives you that in all coordinates is the same L. So now we can define exactly the same relation, but now for any S. What do I do? No. It's a mess. Okay, let's try to go from end to the beginning. So 0. Okay, so if you take Lagrangian function, differentiate it with respect to S, it's certainly 0 because it doesn't depend on S. Now, L of this Lagrangian function is the same as has the same value as Lagrangian function with new coordinates. These do depend on S. So they do depend on S. So we can, so Q prime depend on S and this depend on S. So now we can open this derivative as a chain rule. So first this derivative, then this derivative. So it will be first will be derivative with respect to all coordinates. Prime. And then dq prime, which you put here, right? Yes. And the next sum will be with respect to derivative. I. And this second derivative, right? So it will be second derivative, which is this with respect to S. So it will be ds dq prime dt. So I just wrote q prime dot as a straight derivative. So what do we do next? So with the next, first we remember that by Euler-Lagrange equation, so this is exactly d dt. No. What I'm doing. Yeah, this is correct. This is exactly d dt, the L dqi dot. Right. Yeah. So the Euler-Lagrange equation that this minus this is 0. Very good. And with this term, we can switch derivatives. Derivatives, they commute. So we can write d dt, dq prime, and q prime is hs ds. So what you get at the end is a sum dl dq prime I dhs ds plus dl dq I prime dot well, sorry. So this, right? d dt plus dl dq dot I prime by d dt hs ds. Just copy it. And then you see that this is a full derivative with respect to time. So this is exactly d dt from what? From this multiplied by that. Yeah, because it's just how you differentiate the product. So you differentiate the first term plus you differentiate the second term. And this is 0 because it was 0 from beginning. So this is, which means that this value is conserved. Along trajectory, along every solution. But this expression is slightly weird because the first term is written in terms of prime variables. The second term is in original variables. So how we go back to just single variables is putting s to be 0. When s is 0, then the transformation is trivial. Right? So this gives you just function of q dots, and this is function of q. So this becomes exactly S, C. So you have to, well, proof is short, but have to kind of think several times maybe in order to see. So this is just some play with the derivatives, putting it in the right way, and in one place you use Euler-Lagrange equations. In order to, so where you substitute q derivative with q dot derivative, and then it gives you full derivative with respect to time. So you see, you start with derivative with respect to s symmetry variables and with respect to derivative with respect to time by this manipulation. And this means that independence of Lagrangian with respect to s implies the independence of the conserved variable with respect to t. So that's the whole story. So now, what this is useful for. So I said that essentially it is true, or we expect it is true, that all conserved quantities that we have in natural systems, they come from this kind of argument. Maybe from some transformed form or version of this argument, or more advanced, but from this argument. So the symmetry gives you conservation law, and if you have conservation law, look for symmetry, continuous symmetry. So, and then we'll make a couple of examples. So first example. So first example will be linear momentum, or just momentum. So we already have symmetries from the very beginning. So we have a Galilean group. And Galilean group, all of its symmetries, the main symmetries in the Galilean group are continuous symmetries. So it's translation in space, translation in time that we will speak separately. Rotation is also continuous symmetry because for any real angle. And Galilean transformation does not count. So let's first start with the translations. So we have three coordinates. So let's take translation along axis x1. So it's in other words, you can say that this is homogeneity along direction x1. So what we have is we have that we demand that the Lagrangian function does not depend on a choice of origin. So our function x, it depends on x0, and it maps x to x plus x0, right? So our transformation changes coordinates system to another point, and it should not affect Lagrangian function. That's what we ask for any isolated system, and it depends on the continuous parameter x0. So x0 is a real number. So we are ready with the system. So we have material points which are, so let's index them with alpha. So it's A, B, C, and so on. And this is, of course, applied to all points, but with the same change x0. So x0 is our S. So let's put it that way. It's our S. So this transformation should not change Lagrangian. So okay, so let's compute what is this. What will be this? C is by definition this quantity in arbitrary coordinates, so any generalized coordinates can be used. Qi, so here should be Hi, of course, right? So Qi is changed by the component Hi. Well, here. So this is for arbitrary generalized coordinates, but let's compute it for normal coordinates of all material points. So whenever we have material points, so this is sum over every point. And here we only change the first coordinate. So we only differentiate it with respect to the first speed. And then this function with respect to S is 1. We don't need even put S equals 0 because it's automatic already. And now remember that the derivative with Lagrange with respect to coordinate is always mass by velocity in this direction. So this derivative of Lagrange always is this quantity. This we had before. And you see that this is nothing else as a what's known to be first component of the momentum. So this is C1, C, and then so do the same for coordinate x for other two coordinates. So then we have that P, which is vector of P1, P2, P3, which is defined as a sum of all masses by all velocities, is conserved in any isolated system because of Galilean symmetry group. So any isolated system Lagrangian should be invariant with respect to Galilean symmetry group. So if Lagrange doesn't change, automatically it means that this sum will not change in time. So somehow it's actually a rather long way to come to the momentum, because what you can do, you can take equation Euler-Lagrange for any system of point masses which satisfies this Galilean symmetry group. We know what is general form of this equation. It's just verify that this is conserved. So that would be just straight way, but that's not a conceptual way, because why it is conserved. So it turns out that it's conserved not because it is coincidence, but because of the group with symmetry, because of the symmetry. So symmetry just demand that it's conserved. And this can become a bit more general. So this can apply to the system which are not isolated anymore. So for example, very typical example, for example, you can consider, tube, infinite tube, with free particles, with particles which just somehow move inside. And what means tube? Tube means that tube is described by potential. So tube means that it's 0 inside and infinite outside. So consider the potential, which in the limit, so it's 0 inside, then very fast changes to infinity outside. And what it means is that whenever particles come to the boundary, there is a very big force at putting it inside. So this is this is exactly what's called what is rigid boundary. So, and then you can consider whatever system of particles inside with whatever interaction between them. You know that what you know. So we know that. Let's put coordinate system. So let's put z upwards and x here and that y here. So you know that potential is not invariant with respect to translation in x and y. So the px, py are not conserved. There is no reason for them to be conserved, because we don't have a translation invariance in x and y. But in vertical direction, in z direction, we still have an invariance of Lagrangian. So pz is conserved. So in that way, it's just looking at the system, looking which are the symmetries are broken, which are not. You can translational symmetries which are broken, which are not. You could just directly say which momenta are conserved, which are not. So you don't need to derive. And this is very general. So you see that it doesn't depend on interaction between particles. It's just important that all the interactions, they are invariant with respect to translations. Interactions is that all the potential energy should be invariant with respect to translations. Automatically, in this direction, you get conserved quantity, which is momentum. Very nice. And from momentum, you get a natural concept of the center of mass. So you can define the center of mass as a coordinate which is sum of the which is essentially the momentum defined by sum of the mass, by total mass. So momentum defined on the total mass. Oh, no, sorry. So what I'm telling. So let's derivative will be this. So let's define center of mass as sum of the coordinates of all points weighted with their own mass, and define it by the total mass. So this is called center of mass. So why is it convenient to do so? Because derivative become momentum divided by the total mass. Is conserved for isolated system, which means that center of mass of isolated system moves uniformly along a straight line. So you connect center of mass naturally with momentum. And of course, for this system, it does not apply because we have some outside potential. But for this system, it applies along z direction. So for along z direction, you can define the center of mass in z direction, and it will be just, it will also move with constant speed. So you see that there is putting in symmetry, you gain conservation law, and so it's kind of positive way of looking at that. And also, breaking the symmetry, you break the conservation law. So for example, you don't want to conserve momentum. What to do? Put a wall in this direction, or put something which breaks the invariance in this direction. You know that you don't conserve anymore the conserved quantity, which is also a useful trick, because this trick is one of initial tricks that how you start statistical mechanics. You break some of the symmetries and leave only the energy. Okay, so this is one example. So let's see the second example. I keep this, so it's. So the second example is related to the second type of transformation in the Galilean group, which is rotation. So rotation is kind of not such a simple group, so you cannot. It's hard to write single expression for rotation, but you can always see rotations as a rotation with respect to one axis, a rotation with respect to second axis, and third axis. And with this combination, you can combine with any rotation you like. So let's, and we will see that this will give us angular momentum. So this is related to now to rotations in space, where before linear momentum was associated with translations in space. So let's rotate around axis z first. So it means that we will rotate it in a plane xy. Oh no, that we use x3, x1, x2, and we rotate it with angle psi, and this gives us new coordinates. Okay, and then we have a point which has coordinates in previous system of coordinates and then primed coordinates. So now as our S is psi, right? So our parameter of rotation is psi. And what H psi does, it takes every pair of coordinates, and it maps it to what? To remember how from geometry how we compute it will be x1. New coordinates will be in new coordinate systems. The primed will be x1 cosine psi plus x2 sine psi minus x1 sine psi. So this expression, and this is for all material points, so it means that we have to put alpha everywhere. So this is how we change coordinates. So we had coordinates of all material points, and now we have a symmetry which rotates all of them by angle alpha in the around axis, third axis. Okay. So then we can compute what is corresponding conserved quantity. So we call it M3, because we rotate around axis 3, and we take it with sign minus. No? If C is conserved, minus C is conserved. So let's just convenient to do it with minus, which is minus, and then sum over all points. That expression, right? So it will be dl with respect to dx1 alpha dot, right? dh. So this component I will be 1 alpha or 2 alpha. So these are new coordinates. Then 1 alpha ds plus dl x 2 alpha. Yes. I just wrote this expression, but with respect to new coordinates. So this is minus sum over the same thing. So now remember that this is mass by velocity. And this we have to compute. So this we have to compute. So it's this line with respect to s. So and our s is psi. So this derivative with the psi from this expression. So let's just compute it. It will be minus cosine with respect to psi. It will be minus sine. So it's x1 alpha sine plus x2 alpha cosine. So this is first term, and the second term is the same story, but now we differentiate the second line. So it will be minus alpha cosine psi minus psi. Psi equals 0. And when you put psi equals 0, sine is 0, and cosine is 1. So this gives you minus. So let's put this minus inside. So it will be. No, okay, let's just keep one first minus. Will be m by this x12. And then it will be minus this expression. And this is sum m alpha. Then we switch them x to alpha dot alpha. Okay, so such a reasonably short expression. So now you do the same. Do the same for rotations around other two axes. Okay? So then you rotate with respect to each axis, you get something like this. And this gives you 3 conserved quantities, which form a vector. And this has a form of let's write it down. So there will be M alpha in front. For example, here the last will be, as we already defined. And then by switching 1 with 2 with 3, you can guess the other ones. I never remember it. And then you can recognize that this is the cross product of the two vectors. Mass by x coordinate velocity. So this is exactly what's called linear momentum, or angular momentum. So the conclusion is the angular momentum is conserved in any isolated system. So if you write the system which has because of the Galilean invariance, Galilean symmetry group. So if you say have a system which has a Galilean symmetry group, which those equations are invariant with respect to Galilean symmetry group, automatically angular momentum, vector of angular momentum is conserved. Again, it can be broken if our system is not isolated, but there are some external forces or external external forces, in that case like external potential, then it can be broken. So if you break the rotational symmetry, so if rotation is not anymore symmetry, then of course this momentum along this direction will not be conserved. So already you can see that in this configuration, of course, rotations, symmetry for rotation with respect to x and y axis is broken. But we still keep the symmetry with respect to z axis. So we already can just say that whatever interaction you have, mz is conserved. That is conserved. Of course, as I said, that you can just directly use equation of motion and take this momentum expression for momentum and just directly from Euler-Lagrange equation to show that its derivative is constant. We take a longer way, but in compensation we connect it with the symmetry. So probably once exercise I exercise, so just form. So consider the system between the two rigid infinite walls. So all particles are inside. So they kind of move, interact with each other, whatever it is. And now so our potential for the wall is 0 between two planes, and infinity outside. In that case, particle cannot cross, because we will see that it cannot cross because energy will be conserved. We didn't talk about this, but this is a way how you formalize the symmetry between two walls with essentially what's called with elastic reflection from each of the walls. So we have this system, and let's put let's write. So we have a x coordinate along the planes, and x1, x2, x3. So x3 will be orthogonal x1, x2 along the plate. So let's see what is which components of the linear momentum will be conserved first. So which components of the linear momentum conserved first? So linear momentum is translational symmetry. So we should see that with respect to which translations this potential is conserved, right? Yeah, so we have two components of momentum conserved. And what about angular momentum? And empties. Because why? Because translation with respect to first and second direction do not change, do not move. Plates remain in the same place. And also, if you rotate it with respect to up vertical axis, plates already are the same, do not move. So we don't change the potential. We don't change, which means that we don't change Lagrangian. And automatically we know that this frequency will be conserved. We don't need to check it. For whatever system inside it will be true. Okay. So I think that's it. So tomorrow we have to, so there is one more symmetry which is left untouched, is homogeneity of time. So time, which means that we can change time. And this is not included in the formulation of the Noether theorem as we did now, but we can make some generalized version of the Noether theorem. There are different ways how to do it, I mean different derivations. But anyway, the conclusion will be that it will give us the one more conservation loss, which is conservation of energy. So conservation of energy is direct consequence of the homogeneity of time. So whenever you break homogeneity of time, you put some potential which changes with time, which, for example, our pendulum with moving support. This is something where time explicitly comes to the Lagrangian. We break the energy conservation. So we already don't even have to think. So the energy will not be conserved in that system because Lagrangian depends on time. Whenever Lagrangian does not depend on time, we conserve energy because of the Noether theorem. Okay, so I think that's it for today. So see you tomorrow.